systems.
All right, so I'd like to thank the organizers for having me here. It's a great pleasure. It's a very nice center and the talks have been very instructive. So just as curiosity, the name of my university is really Yeshiva, like God Shiva. But I don't know if the words are related. Just for you to know, what I know is that Yeshiva refers to any Orthodox Jewish school or Orthodox Jewish university. So some of the students that go to Yeshiva University become rabbis. And the other thing that I know is that Shiva, just the word Shiva in Hebrew means 7. So when someone dies in a person's life, in a person's family, he says, I'm going to sit Shiva, which means he's going to mourn for 7 days. I don't know if there is any relationship. Okay, so the results I'll present here were obtained with these previous postdocs. Jonathan Torres, he's now a professor in Mexico, and Marco Tabra, who got a position, it's a job in a company in Brazil. So he's becoming pretty rich. So I'll be talking about quantum systems. They have many interacting particles, and at odds with this conference, they are isolated. We are trying to see now what happens once we include decoherence, but it's not in the results that I'll be showing to you. Okay? And what we do with these systems is we take them out of equilibrium, far from equilibrium, and there are several questions that we have been asking. So some examples. We want to know how this dynamics depends on the initial state, on the strength that takes this system out of equilibrium, the strength of the perturbation, how the dynamics depends on the Hamiltonian, if I have short or long-range interaction, if my system is integrable or chaotic, how the dynamics depends on the proximity of a critical point. For example, how the dynamics depends on how it changes as I approach a transition to a many-body localized phase. So this metal insulated transition. How fast these systems can evolve. Can we reach a quantum speed limit? And do we have different behaviors at different time scales? Well, the idea is if you wait long enough for the systems, they're very complicated. Even though they are isolated, they eventually equilibrate. They may even thermalize. So thermalization has been the subject of some recent review articles. This is ours. There is also the review article by Marcus and Anatoly. There is an older one by Zelevinsky. But I'm not going to talk about thermalization here. I'm going to focus on just some aspects of the dynamics. But of course, if you want, we can discuss more about these results. Okay, so the idea is all these many different questions that I'm asking here, they are not just theoretical questions. There is a lot of experimental interest in non-equilibrium quantum dynamics, and we've been seeing this, also in the viability of thermalization. So let me mention just some of these experiments. Non-equilibrium quantum dynamics has been studied for a long time in NMR. That's the whole idea of this echoes. More recent, we have these experiments with cold atoms, optical lattices, and we heard about them yesterday, so highly controllable systems. We also have the experiments with ion traps, and here a big sensation is that they can tune the range of the interaction, so they can have very long range interactions. And we've heard throughout this week other possibilities. In some of the systems that are studied in these experiments, well, these are experiments where coherent evolution can be studied for a long time, and some of these systems are well described by the Hamiltonians that we'll be talking about. So we'll be dealing with one-dimensional systems of spins half. We'll have Hamiltonians such as this one. So this is a simple one that we can have, the sigma Pauli matrices, and this is the just coupling the x and the y direction. So this is the flip-flop term. What it does is to move the excitation along the chain, so it's a hopping term. So when I have a Hamiltonian like this, I'm describing a system that is integrable and non-interactive. If we add to this Hamiltonian the Ising term, and if we are in one dimension, I have just couplings between nearest neighbors, this Hamiltonian is still integrable, but now I have an interacting integrable system. It's more complicated to solve. You need the base answer. This Hamiltonian here, because the x and the y have the same strength and the z is different, we usually call it the xxz model. So I'll be saying this one. Okay, but this integrable point is very delicate. It's very easy to break integrability and bring this system into the chaotic domain. I'll tell you a little bit about quantum chaos, but let me just mention some of these chaotic Hamiltonians. So you see here I have the xxz model, and I added a single defect. So I have here a single Zeeman splitting that is different from the others. So the presence of this single defect is enough to bring my system into the chaotic way. Another way, I can have all of the Zeeman splittings, all of these sites with different Zeeman splittings, now randomly distributed. So here I have on-site disorder, and this system can also be chaotic. Another alternative is I add couplings between further sites. So in this example here, you have couplings between second neighbors. So we kept the chain clean, but I have couplings between further sites, and again, it becomes chaotic. So all of these are describing very complicated systems, very complex systems. So most of the results that we can present are numeric. But of course, we would like to have some analytical expression that can guide us, that can guide the studies of these realistic systems. So to try and to get analytical expressions, what we are going to do first is, instead of dealing with these Hamiltonians, I'm going to study full random matrices. So matrices filled with random numbers. So this is an approach very similar to what Wigner did back in the 50s. So what Wigner had is heavy nuclei. So he was trying to describe the spectrum of these heavy nuclei statistically. And the idea was, well, instead of going to all the details of these interactions between the nucleons, let me deal just with a matrix that is filled with random numbers. And the only constraint is that it should satisfy the symmetries of the system that I'm trying to describe. So they are not realistic, completely filled, but it implies that all the particles are interacting at the same time, that short and long range interaction have the same strength, but they allowed Wigner, and it will allow us to get analytical expressions. Analytical expressions that will serve as bounds, as references to the studies of the realistic systems. So just to give you an idea, this is the XXZ model. So I wrote the Hamiltonian on a certain basis, and you see it's very, very sparse, very different from the full random matrix. And in many of the examples that I mentioned, we don't even have any sort of randomness. Okay, so this is the idea. But before showing to you the results for the dynamics, let me discuss a little bit, let me compare the static properties of these two different cases. So I'm going to start with the level spacing distribution. So just a histogram of the spacing between neighboring levels. So I collect all of these spaces, E2 minus E1, E3 minus E2, and so on, and I make a histogram. So when I'm dealing with full random matrices, we get curves that look like this red one. The exact shape depends on the symmetries, but the main idea is that you see there is no spacing 0. So my levels do not cross. They are not degenerate. We have level repulsion. So level repulsion is a main signature of what we call quantum decays. So we have level repulsion. That means the eigenvalues are correlated. The spectrum is rigid. And so that's the idea. If I have a Hamiltonian that gives me level repulsion following a Wigner-Dyson distribution, I'll say that my system is chaotic. And so I pick the levels for a real nucleus, and there you are. You see the Wigner-Dyson distribution. If I pick the eigenvalues for those Hamiltonians that I said they are chaotic, well, again, the Wigner-Dyson distribution. For the Hamiltonian where I have a single defect, or the one where we have on-site disorder, or the one with further couplings between further sites. On the other hand, if I pick my XXZ model, which I said is integrable, then we have many crossings. The levels are uncorrelated, and I have usually the Poisson distribution. Now, which curve I'm going to get depends on the parameters that I pick for the Hamiltonians and on the system size also. So I don't have to have necessarily just Poisson or Wigner-Dyson. I can have something in between. So I can have intermediate statistics. Okay, so let's continue with this comparison. Here what I'm comparing is now the density of states. So histogram of all the eigenvalues. For full random matrices, we have this shape, is the semicircle shape. While for these models, such as spin models or any realistic model where we have just two-body interaction, the density of state is Gaussian. So this is going to be important. These two different shapes will be important for what comes next. What else? How about the eigenstates? Well, the eigenstates of full random matrices, they are just random vectors. Now, all of these coefficients are just random numbers. So they are completely spread out, completely delocalized. There are quantities that we use to measure how much delocalize how big the superpositions are. One of these quantities is the participation ratio. So the idea is you write your state in a basis, and the participation ratio is 1 over the sum of these coefficients to the 4th. So for the full random matrix, they're all random vectors. The participation ratio is just proportional to the dimension of your matrix. So this is an analytical result. And all of them are the same. So there is no energy dependence. All these states are just equivalent. When we move to the realistic systems, well, then things change. It's only in the middle of the spectrum that the states can be very delocalized, because it's in the middle of the spectrum we have many, many states. So in the middle of the spectrum, they can be very delocalized, close to random vectors, but not there yet. No, we don't have the same level of ergodicity that we have in full random matrices, while at the edges, they become pre-localized. And of course, the numbers that we get now depend on the basis that we choose. The other important thing, so this energy dependence will be important for studies of thermalization, for studies of non-equilibrium quantum dynamics. Okay, so this is short introduction for the static properties. I'm going to move to the dynamics. And for the dynamics, I'm going to start with a very simple quantity. And the quantity is this one. We are going to call it survival probability. So it's just the overlap between the initial state and the evolved quantity. So it has many different names: survival probability, non-decay probability, return probability. Just don't call it Loschmidt echo, because that's not right. The evolution here is just forward. There is no back evolution. So if I write my initial state in terms of the eigenstates of the Hamiltonian that is evolving my system, so if I write the initial state in terms of the energy eigenbasis, what we see is that the survival probability is just the sum of these coefficients with these phases, where those e's are my eigenvalues. Okay. Let me write this sum as an integral, where this rho here carries this delta function. So this rho, what it is an energy distribution, but not of the whole system. No, it's the energy distribution of that particular initial state that I picked. So it's weighted by those components. So since it depends on that particular initial state, I'll call it the local density of states, LDOS. Okay, so you have an example. So if I do the Fourier transform of this LDOS, I get the behavior of the survival probability. So the idea is that. So let me now study the survival probability for full random matrices. So it's a theoretical exercise. Okay? So what is the idea? I'm going to pick an arbitrary state, and I'm going to project it into random vectors. Going to project it into the eigenstates of my full random matrix. Okay. First thing that I'm going to do is I'm going to look at the local density of states, and you see here the distribution. Now you see that for the local density of states, I get the same semicircle that we had before. So the local density of states agrees with the density of states. It's just a reflection of the density of states. Okay, so I have my semicircle, so I'm going to do a Fourier transform on that. And we know what it is. It gives us this Bessel function. So this is an analytical expression, which is shown in the figure with this red solid line. And in black, we have the numeric. So you see perfect agreement. So what do we have here? First, a very fast decay that goes all the way to 0, the Bessel function, and then those revivals, partial revivals. So we can study this expression asymptotically. And with studying this asymptotically, we will be able to get the decay of this oscillation, of the envelope of the decay of this oscillation. And this is what you see here. So this decay goes as t to minus 3. So the exponent, the Power-law exponent is 3. So you see here we have the most chaotic system that we can think of, and yet we see the dynamics slowing down and showing a Power-law behavior. So Power-law decay, even though we have full random matrices. Okay, but now I have to be a little careful with this story, because I'm dealing with matrices that are finite. So my survival probability is not going to decay all the way to 0. It will have to saturate at a certain point, because my systems are finite. And the expression is not taking this saturation into account. The other thing is, when I did the Fourier transform, I only took into account the envelope of this distribution. I didn't take into account possible structures, internal structures of this distribution. My spectrum is discrete, my eigenvalues may be correlated. I'm not capturing it with this expression. So to take into account these two things, I'm going to look at the survival probability a little bit more carefully. Okay? So this is the expression for the survival probability. Now instead of a single sum, I'm going to open this square, and I have two sums, in alpha and in beta. When alpha and beta are different, I have this first term, which will determine my dynamics. When alpha and beta equal, I have this term. This is the saturation. So the survival probability evolves for a while, and then it's saturated, fluctuates around this infinite time average. This is the inverse of the participation ratio. And we know what it is for full random. Okay, so this is saturation. Let's come to the dynamics. What we are going to do is, well, I'm going to write the sum as an integral, and this G that shows up there is the spectral autocorrelation function. What we are going to do is, well, since we have random matrices, we are going to do averages over different matrices, ensemble averages. And I'm not going to go for the details, I'm just going to show you the results, but there are details in Al-Hasid's paper, also in books about random matrices, and I have some slides later if you want to see. Okay? So I'm just going to show you the result of this average. So when we do that, we find two terms. One is the one that we had seen before. It comes from that semicircle shape. The Fourier transform of that had given us that Bessel decay with the Power-law decay. The other function that is showing up here is this B2. This B2 is detecting what happens inside the distribution. So this B2 detects correlations, possible correlations between the eigenvalues. And then the saturation point. So this whole expression here is the analytical expression for the survival probability for full random matrix. From the moment I took it out of equilibrium all the way to saturation. So let me compare this analytical expression with the dynamics, with the numerics. And this is what we have. So in red, we have this full analytical expression, and in black, the numerics. And you can hardly distinguish, so they are really on top of each other. So let's have a look at the figure. Initially, we have the Bessel behavior, and you're seeing it here, the Power-law with the exponent 3. Very long times, we see the saturation around this infinite time average, is this dashed line. And in between, you see something interesting. You see that the survival probability goes below this infinite time average. So you have this dip. And this dip is being caused by that B2. And so this dip only shows up if my system has level repulsion, if the eigenvalues are correlated. If I have that Poisson distribution, like the XXZ model, where the levels cross, B2 does not exist, it's just here. Okay, so this dip is known as correlation hole. The correlation hole was studied back in the 80s and 90s. So you have some people from the chaos community, Al-Hasid, Seligman, Weidenmüller. And the way that it was presented at that time was, well, this is an alternative to detect level repulsion, but from the dynamics. So this was an interesting alternative in cases where I didn't have direct access to the spectrum. So they were thinking here about molecules where the line resolution was not very good. What we are doing is we are bringing this subject of correlation hole to these systems, to these many body quantum systems described with spin models or Bose-Haber models. And what is the advantage? Well, in many of those experiments that I mentioned to you, ion traps or cold atoms, sometimes you do not have direct access to this spectrum. Just as a parenthesis, the correlation hole is being rediscovered by the high energy physics community. If you've been following these studies about out-of-time correlator or the analytic continuation of the partition function. So they are finding again this correlation hole, they call it a RAM. Okay? They didn't make the connection with this. Okay, but very well what I showed to you here is analytical result, very nice, but for a non-realistic case. So let's go for the realistic scenario, for the realistic systems. And what I'm going to do is I'm going to study the dynamics for different time scales again, piece by piece, to try to make the whole puzzle. So I'm going to start with short times. And what I want to show to you is at short times, the dynamics depends very much on the strength of the perturbation. Okay? To show you this, I'm going to start as this is just an example. My initial state is an eigenstate of this Hamiltonian, the XX. And I'm going to add couplings between second neighbors. So this lambda here is the strength of my perturbation. Okay? So you see that if my initial state and the eigenstate of this Hamiltonian, let me say this again. If this lambda is very, very small, so my perturbation is very, very weak, this is not very interesting because my initial state is very similar to one of these eigenstates. No? So the LDOS will be very, very narrow. The Fourier transform of that will give me a dynamic that is very slow. Okay, so the perturbation is very, very small, nothing very interesting. This is what you see here, almost a delta function, and then very slow decay. But let's make things more interesting and increase the perturbation. As we increase the perturbation, my initial state gets further from any of these eigenstates. The LDOS broadens. Broadens eventually becomes Lorentzian. So this is the regime of the Fermi-Golden rule. The Fourier transform of that gives us this exponential decay. Let me increase the perturbation even further. And then what we see is that the LDOS broadens even more and becomes Gaussian. Fourier transform of the Gaussian gives us this Gaussian decay. Okay, so I have a decay now that is even faster than exponential. And where is this Gaussian coming from? Well, remember the density of states of these systems with two-body interaction is Gaussian. So this is just a reflection of the density of states. One detail, these very fast behaviors that we saw, exponential and even Gaussian, they don't show up only because my final Hamiltonian is chaotic. The same fast behaviors can show up also when the final Hamiltonian, the Hamiltonian that evolved the system is in. Okay, so initial, very fast behaviors is just a sign of strong perturbation, not of level repulsion, not of chaos. Okay, now what comes next? To study what comes next, what I'm going to do is I'm going to focus on this Hamiltonian here, not so the XXZ with on-site disorder, because then I can do averages over disorder. The thing is, as we move to longer times, instead of having many fluctuations, finite size effects become important. So as I do averages over disorder realizations, I can smoothen my curves. So I'll do averages over these different realizations, and also averages over different initial states. So the initial states that we are going to consider now are these ones that are more accessible to the experiments, like the experiments in optical lattice. And what we have is, on each side, either the spin points up or down in the zeta range. Okay, but different configurations of this kind, because I'm going to be doing average. So the total average that we deal with is 10 to 5. Okay, now, when I have a state like this, evolving according to this Hamiltonian, is as if I had started with an easing Hamiltonian and then had added this couple. So you see that I have very strong perturbation. And if I have very strong perturbation, what I expect initially is a Gaussian decay. And this is what you see here. So this initial Gaussian decay. After that, you see many different curves. Each curve is for a different value of the disorder. So each curve is for a different value of the disordered strength. Okay, and you see that we have Power-law behaviors. And you see also that I separated these curves into green curves and red curves. And now I want to discuss the two cases. The green ones have Power-law exponents smaller than 1. The red ones have Power-law exponents larger. So I'm going to start with the green one. But to explain to you these different regions, let me characterize a little better that Hamiltonian. So the disorder Hamiltonian. Okay, so this is going to look at level statistics, the level of delocalization of the eigenstate. So this is something that we did back in 2004. So we studied when we have a Poisson distribution, when we have a bignotized, when my eigenstates are localized, when they are delocalized. We also study entanglement for this Hamiltonian concurrence. Forget about entanglement. I'm going to focus just on these two. Okay? So what do we have here? If my disorder is just 0, does not exist, I'm back to the XXZ. integrable model, Poisson distribution. So Poisson distribution is indicated here with this quantity eta being close to 1. Okay? I increase the disorder from 0, and we see that my Poisson is going to get more and more deformed, and eventually I'll get a good Wigner-Dyson. So good Wigner-Dyson means eta close to 0. Okay? But if I keep increasing h, what happens is h now becomes bigger, larger than the coupling parameter. I see that I get away from the chaotic region again and go into another integrable point. So what is going on here? Well, here we are going into an insulating phase. My eigenstates are becoming localized in space. So we can see this integrable-chaos-integrable transition with the participation ratio also. So here in the chaotic region, the participation ratio is proportional to the dimension because the eigenstates close to the middle of the spectrum, they are close to random vectors, they are chaotic states. But if I keep increasing the disorder, so that the disorder is larger than the coupling, what happens is the eigenstates become more and more localized. So the participation ratio is no longer proportional to the dimension of the Hilbert space, but is now dimension to a power d2, which is smaller than 1. Okay, so let's go back to that figure. This is the d2 that you are seeing, and this d2, which is smaller than 1, agrees with this Power-law exponent. Let me show to you how we compare these things. So the idea is first we pick our eigenstates, we pick our initial states, and look at the participation ratio for different system sizes. And we do so a scaling analysis to extract the d2. So everything here is just static. I extract this d2. Then I compare this d2 with this Power-law decays for different system sizes, and I see that it improves as the system size increases. This agreement gets better and better. So what is this d2? What is this Power-law exponent telling us? It's saying that the eigenstates are becoming more localized. It's telling us that the eigenstates, remember this is that correlation function, so it's telling us that the eigenstates are becoming correlated. I need correlation here to get a Power-law decay. So my eigenstates are becoming correlated, my eigenstates are becoming fractal. This d2 is what we call the fractal dimension. Okay, so we understood this behavior. I can also even use this d2, this fractal dimension, to detect this transition from chaos, from this metallic phase, to that insulating, to that localized phase. Okay. So this is this region. Now what happens in the red region? The red region is the chaotic region. Okay? And the Power-law exponents that we get here are larger than 1. So where is this coming from? The idea is these exponents are similar. The idea is similar to what we had for the full random matrices. Remember the full random matrices, we had those semicircle shapes. So my spectrum was bounded. And so my spectrum ends at a certain point. When I take these bounds into account, I got the Power-law exponent with exponent 3. Well, my spectrum here is also bounded. It's also bounded, but I have a Gaussian. But no, because this is the realistic system. But if I take these bounds into account when I am doing the Fourier transform, you see that I don't have just Gaussian decay, but I have a combination with this error function. If you study this asymptotically, you see that we have a Power-law decay with exponent 2. So not 3, but exponent 2. So this is the source of this Power-law decay that we are seeing here, the bounds in this way. So we explained the short behavior, this Gaussian because of strong perturbation. The Power-law decay is coming up later. And what is next? So what happens here? I chop my figure. What comes next? To show what comes next, here I have many different panels. So going to very long times now. And what we see? Very small h. Remember, it's one of those integrable points, the clean integrable point. So there I have Poisson distribution. The eigenvalues are uncorrelated. What do we see? That after those decays that I already described, just fluctuations around the dashed line, which is the saturation line. When my disorder is very large, so I'm close to that other integrable point where my system is becoming localized in space, Again, after the Power-law decay, just saturation. But in between these two extremes, in those regions where I have intermediate statistics, where I can even have good Wigner-Dyson distribution, you see that there is one more thing. After the Power-law decay, I have this dip, which is the correlation point, okay? Also for this realistic. So this dip is really deep when I'm in the chaotic region, when I have this nice Wigner-Dyson distribution. When I get intermediate distribution, intermediate statistics, as my age goes on increasing, what you see is that it becomes less and less deep, it fades away, and it gets postponed to longer times until it eventually disappears. So I can also use the depth of this correlation hole, which is a signal level repulsion. So I can use this depth as a way to detect this transition. Very deep here is chaotic, is metallic phase, no depth anymore, insulated. But you see that the correlation hole detects any integrable chaos transition. So I have the transition from chaos to localization in space, but I also have the transition from chaos to my integrable clean XXC model. So I could say localization now in a mean field. Okay, very nice. We have all these different behaviors. We understand them, but we would like to have a complete expression just as we had for full random matrix. So that's what we are after. And this is what we are proposing here. So what we have here is, I'm trying to get a single expression for the realistic system that is the most chaotic one. Because I'm using what I got for the full random matrices as a guidance. So what I got for full random matrix is motivating the expression that I'm proposing here. So remember, for full random matrix is what we had. Initially, we had a Bessel decay with the Power-law behavior with exponent 3. Well, what we are proposing now here is, for the realistic system, a Gaussian decay with Power-law exponent 2. Later, we had correlation hole. Let's put the correlation hole. And finally, saturation, saturation. So this is an expression with a single fitting constant, and we are trying to match the most chaotic scenario of the realistic system. And these squares are for this analytical, not analytical, expression. And below you have the numerical results. So let me isolate this curve. Here it is. So you have a very good. What did we use for that B2? The same expression that we had for full random matrix. Look, this is in red is the B2 for full random matrix, it's the analytical expression, and in black is for numerics for the realistic systems, and it's pretty much the same. So we were able to match this very well. Okay, so this is the expression that we were after for the realistic system. Yeah. This one? This one? Yeah, but then here the disorder, the H is large. It's already larger than the coupling parameter, so we are in this region. The JZ, without easy interaction anymore. Okay, in one dimension, if you have just the hopping part with disorder, that's Anderson localization, so for any disorder, you should have localization already. I didn't do that, but there should be at least this initial decay. I'll talk about entropy. You may have heard about the results for the entropy. Okay. So let me see anyway. So you may have heard about these results for entanglement entropy for Anderson localization 1D. So what people saw there is an initial increase and then saturation, nothing else. While when there was interaction, was this initial increase and then a logarithm behavior and then saturation. So that initial increase is the same time interval where we have this initial Gaussian. So at least the Gaussian should show up. I have the entropy, so yeah, I think we'll have time to show that. So this one, what I have is the Gaussian, then the Power-law. this region for the Power-law behavior is the same time interval we get the logarithm for the entropy. Okay. Oh, yeah. No, careful with that. This is the quadratic behavior that you're thinking about. The quadratic behavior, okay, good that you mentioned that. The quadratic behavior shows up for any. That's just perturbation. Huh? So, where I have this is what you're saying, right? So if you just do an expansion, you have this quadratic behavior. Huh? So this quadratic behavior shows up even when I have the exponential. This very short times is just this quadratic, and then it switches into the exponential. But here, what I have for the Gaussian is long. It's beyond. If I put just the quadratic, it's here. The width is the width of the LDOS. Yeah, that's what you have. Okay, so where was I? So we got already that expression, the full expression for the realistic system, but that's for the survival probability. What we did was to look also at observables. So one of the quantities that is measured in experiments with optical lattice is this imbalance. So the spin imbalance is this correlation. It is the on-site magnetization for different sites. And there what we have also very fast initial behaviors, Power-law, and the correlation also shows up. So the correlation also shows up in these observables. Okay, so let me explain what I have here. This is the result for full random matrices. So I can get analytical result there. And these curves are for the realistic system. And H is increasing. So when I'm deep in the chaotic region, I have a very nice correlation. And again, I can match this correlation hole with that B2 function. So you see good agreement for a very long time. So even if you experimentally you don't have direct access to the survival probability, well, you could also detect this correlation hole from an observer. Okay, so this is the results for survival probability, imbalance, and then I wanted to mention a little bit the entropies. But if I don't have time, if it beeps, then I stop. You tell me. So for the entropies, I wanted to show results again for different time scales. So short, intermediate, long, and saturation. So let me give you the results and comparing with the survival probability. So short times, when the perturbation is very strong, for the survival probability, for the imbalance, we saw the decay can be very fast, exponential, even faster can be Gaussian. What do we have for the entropies? This linear increase. Okay, let me go later. I go later, what we saw for the survival probability, imbalance, Power-law decay. And we saw that Power-law decays with D2, we saw that Power-law decay with D2 matching the exponent, so D2 is smaller than 1. What happens for the entropies? That's what he was asking. For the entropies, we have logarithm increase, slower. Okay? And I want to tell you more about this. Long times, for the survival probability imbalance, we have the correlation hole, but only if I have level repulsion. For the entropies, you see also a little correlation bulge, and then the saturation. Okay? All right, so let's go for the entropies. I'm going to look at two entropies. The very well-known entanglement entropy that has been so much used in quantum information, the studies of localization. What is the idea? You have the reduced density matrix. You have the density matrix for the whole system. Trace out some degrees of freedom. You have now the reduced density matrix. And then the von Neumann entropy for the reduced density matrix is what is known as entanglement. So it measures the entanglement between the portion that survived and the portion that was traced. Good. Let me show results also for another entropy, which is the Shannon entropy, also known as information entropy. Let me say a few words about it before I show you the results. Okay? So the Shannon entropy is just another measure of delocalization. It's just another way to measure how much delocalized my states are. So I have my state in a certain basis. Remember, this was the participation ratio, this sum here. Well, the Shannon entropy is this other sum, where I play with this coefficient squared and the log of those coefficients. If you write the state that you're studying in the energy eigenbasis, so you're thinking about, So you think about Quench Dynamics, no? So you pick your state and write in the energy eigenbasis. The Shannon entropy becomes, well, it's often called the diagonal entropy, which is the entropy that Anatoly introduced and has been much used in studies of thermalization. Fine, but up to this point, I didn't show to you any dynamics. We want to use this entropy to study dynamics. So what I'm going to do is, instead of these components here, these static components, I'm going to use these probabilities. So I have my initial state, and this W is the probability for finding my initial state in another basis vector of the basis that I picked. So then I can have dynamics. Okay? So this is what I'm calling Shannon entropy. So I'll go quickly now. So here is just a plot to show you short times. Okay? So here is Shannon entropy. This is the entanglement entropy. And you see, linear increase. I'm focused just on the short time. Okay? And this linear increase shows up for chaotic models, shows up also for integrable models. So fast initial dynamics is just a signature of perturbation, not a level repulsion. What comes next? Again, to study later times, I'm going to use the disorder Hamiltonian. And I'm going to focus on this region between chaos and localization. So this region where I have intermediate level statistic, where my eigenstates are fractal. And as we already discussed, in this region, what was much discussed in the studies of localization, you have a fast linear increase, and then it slows down, becomes logarithmic. For the entanglement entropy, here I'm showing results for the Shannon entropy, and you see the same thing. Okay? Fast behavior, and then this logarithm. The advantage of the Shannon entropy is that you don't need to do any trace. You deal with the whole system. It's better for statistics, easier to compute. Okay, so we are seeing the same logarithm behavior, and what is nice is the slope of this behavior is the D2. Okay? So the D2, the fractal dimension that was capturing the Power-law exponent, also captures the slope of this logarithm. Okay, and later, we have some sort of signature of the correlation hole. For the entropy, you have a little bulge. But these results are not so good because this is a system without averaging, so I'm not going to spend much longer on that. Let me just go for the summary. Okay, there is a whole bunch of things there, but let me just summarize with one main idea. What we are trying to do is to describe the dynamics of realistic systems, which are very complicated. But it would be nice to have some analytical expression to guide this study. So to get analytical expressions, we have two extremes. One is go for the integrable models that will allow us to get analytical results. The other extreme, that's what we did here, let me go for the most chaotic case of full random matrix and see how much of these extremes survive and how much of these extremes can help us to describe the realistic system. And next will be the coherence. So stay tuned. Thank you for your attention.
Questions?
You should see correlation hole in any system where you have level repulsion. If you see a Wigner-Dyson distribution for your spectrum, the correlation hole will find out. But we are going for very long times, so you cannot do DMRG or things like that. So to do exact diagonalization, we need matrices up to 20,000, around that. Beyond, we cannot. So for those systems where we have half filling, L16. But we compensate for the small system size with big M.
Thank the speaker again. This is the end of the session today.